Okay, so L'Hospitals Rule. So L'Hospitals Rule is nice. So it's kind of, we're going to go back to evaluating limits, basically. So it's a technique for evaluating limits, and it's especially useful for certain types of limits, like when you have trig functions, often, it's really good. If you have power functions, it's really good. If you have exponential functions, also really good, really useful. The nice thing is that it's useful, especially in the times when doing our regular techniques is very challenging or impossible. So that's nice. And it's one of the applications of derivatives. So let's write it down. So L'Hospitals Rule. Let's suppose f and g are differentiable at a. And continuous at x equals a. Or sorry, not continuous at x equals a. Continuous around x equals a. Then, well, no, not then. Okay. Okay, so I'll suppose also we have an indeterminate limit, and this is really important, of type 0 over 0 or infinity over infinity. Okay, so this is the key thing here. So we have to make sure before we even think about using L'Hospitals Rule, it absolutely, positively must be 0 over 0 or infinity over infinity. If it isn't, that doesn't mean we can't use L'Hospitals Rule on this particular limit. It just means that we would have to reorganize things and maybe do some algebra before we do it. Okay. Okay. So if that's the case, then we have that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. So you're basically looking at, instead of looking at the limit of the quotient of the two functions, you say, okay, well, get the derivative of those two functions and then take that limit, see if it's easier to find. Notice, are we using the quotient rule here? No, right? You're getting the derivative of the numerator, derivative of the denominator, and that's it. So there's no quotient rule involved here. And there are some times when getting the derivative makes a function more complicated, but often it makes it simpler, right? So like, for example, if you have like a power function like x to the third or x to the fourth, x to the fifth, what happens every time you get its derivative? Yeah, the degree goes down every time, right? So it gets simpler every time you get the derivative. So that's why sometimes it's useful. Okay, so proof. We can prove a simple case, but I am going to refer you to the mini lecture. Okay, so you guys can watch it on the mini lecture. It's short. But then we get to do more examples. So let's do some examples. Okay, exhibit A. Evaluate the limit as x approaches 0. So an old friend. You guys remember this guy? So do you guys remember when we were looking at limits, we did this one. Do you guys remember how long it took us? We had to use the squeeze theorem. we did this, like, you guys remember we like drew this picture and then we did like three regions. You guys remember all that stuff? And we compared the area of the three regions to set up our inequalities, and then we did the squeeze theorem. It took us like 30 minutes to do the whole thing, right? You guys remember that? Yeah. Okay. But thanks to L'Hopital's rule, this is a trivial problem. So notice that, so always very important. So really, really important. Before you do L'Hopital's rule, what did we say? It must be indeterminate, 0 over 0, or infinity over infinity, right? So remember, so if we go back here, so maybe I'll do this. Let's do this. Let's put a star here. If indeterminate of the form, so do you guys remember some of the other indeterminate forms? Infinity minus infinity. That would be 0. We had 1 to the infinity. This is one that we'll see a lot. 0 over 0, infinity minus infinity, 1 to the infinity. There are other ones, but these are the main ones that we see. What does this mean? You must first rewrite using algebra. Okay, so this is very important. You must first rewrite using some algebra. So this is one of the biggest mistakes that I see. Students will say, oh, I learned this awesome new rule, L'Hopital's rule, and you just start using it. But if you don't use it when it's the right time to use it, then you'll end up getting an answer, but it'll be the wrong answer because it wasn't the right place for it. Okay. All right. So anyways, so here, what's the first thing we do? We plug it in, right? So what happens when you plug in 0 here? 0, 0. You get 0 over 0. Okay. So then, can I use L'Hopital's rule? Yes, right? Okay, good. So what do I do? So what I like to do is I like to put an LH when I'm going to use L'Hopital's rule. So then I remember, oh, I use L'Hopital's rule here. And then I'll say, okay, well, this is equal to the limit as x approaches 0 of, and then here you're going to get the derivative of the top and the derivative of the bottom. So what's the derivative of sine of x? Cosine x, good. What's the derivative of x? 1. Again, notice, did I use the quotient rule? No, right? I did not use the quotient rule. Okay. Now, after that, then what do you do? You can, if it's, if there's more stuff, you can see if there's anything to simplify. Otherwise, at this point, what you should do is plug it in again. So if I plug in 0 in there, what do I get? I get the number 1, right? So this is equal to 1. 1 and done. That's it. So easy, right? So pretty awesome. Okay, let's try another one here. So one that's a little bit more complicated. How about the limit as x goes to infinity of ln of x divided by x? Okay, so this is one that, for example, if you, well, we always do the same thing, right? You plug it in. So plug in, well, you imagine like you plug in infinity in this case, but what's the limit as x goes to infinity of ln of x? So where does ln of x go? It just goes to infinity, right? So the ln, the natural log function, looks like this. So so as x goes to infinity, ln of x goes to positive infinity. Slowly, but it goes to positive infinity, right? So then what kind of limit do you have there? Is it indeterminate? Sure it is, right? It's infinity over infinity. So, okay. So can I use L'Hopital's rule? Yes. I can. Good. Okay. All right. So then I get the limit. This is equal to the limit as x goes to infinity And then you just get the derivatives, right? So what's the derivative of ln of x? 1 over x, good. What's the derivative of x? 1. Okay, and now if I get the limit of that, what do I get? 0, right? Because as x goes to infinity, 1 over x goes to 0. Now notice if I would have tried to do this, I know you guys are probably a little bit rusty at this point with your limit techniques, but what technique would we use to evaluate that limit? So typically when we were doing like limit as x goes to infinity and you had a power function, typically you would divide by x to the highest power, right? Which you can do here, but what would happen? What would you get if you divide by x? I mean the highest power is 1, right? So you would basically divide by x, which would give you 1 in the denominator, but then what would you have in the numerator? ln of x divided by x, which is exactly what you started off with, right? So does that help you? No. Are there any other, like can you factor it, for example? Can you use an identity? No, right? There's no way forward for this limit. There's really no algebra simplification that we can really think of doing, right? So it's good that we have L'Hopital's rule, because otherwise we would not be able to evaluate this limit, right? Right. Okay, all right. You guys want to try one? Ready? Are you ready to try one? How about, let's see. How about, let me see if I can find a good one here for you. Okay, how about the limit as x approaches 0 from the positive direction 1 minus ln of x over e to the 1 over x. Okay, give it a go. Okay, so we decided it is infinity over infinity, right? Question, what if I had minus infinity over infinity? Would I still be able to use L'Hopital's rule? You can. Yeah, so the sign of infinity doesn't really matter. Because you can always factor out the minus 1 and you would have, because it's just a constant, right? So you would have, so if I have, if I factor out the minus here and then I would have infinity, positive infinity over infinity, then it would be the same thing. So you don't have to worry about that. Not that this one is minus, but if it was, that would not be an issue. Now, if you get infinity over 0, for example, can I use L'Hopital's rule? There, no, right? Okay, all right. So there's a little side note there. Okay, so anyways, so if we use L'Hopital's rule here, so what would we get? We would get the limit as x approaches 0 from the right of, what would I get on top? Negative 1 over x. What about on the bottom? E to the 1 over x times the derivative of 1 over x, right? Which is minus 1 over x squared, right? So maybe you wrote it as minus x to the minus 2, which is fine. And then notice, well, should I do L'Hopital's rule here? Well, you really should not, because if you do, what are you going to get? You're going to have a really messy derivative on the denominator, right? But before that, you should check to see, can I simplify this anywhere, right? Because if you can simplify it, well, then maybe that would reveal something. So what do you notice here? Does anything simplify? Yeah, if you want, you can invert and multiply, right? So like if I rewrite this, let's say, you don't have to rewrite it, but if you want to, you can rewrite this as, so e to the 1 over x stays on the bottom, right? And then this one, if you invert and multiply, this would be minus x squared, right? minus, hold on, minus x squared. Okay. Now, when you multiply minus 1 over x and minus x squared, you get plus what? Just x, right? Okay, now is that any better than what you had? Okay, so this is important. So, yes, as long as the condition still holds. So, it's okay to do L'Hopital's rule multiple times, but you have to check to see if it's applicable at every step. Does that make sense? So you should not mindlessly at this point do L'Hopital's rule again because you're not done. You would plug it in now and see what you get. If it's still indeterminate and it looks like L'Hopital's rule would help you, then yes. But if it is not indeterminate, then you cannot use L'Hopital's rule. Okay? Okay, now, so what do we get when we plug it in? 0 over infinity, right? Okay, now is that indeterminate? No, right? So I get, students get very confused with this, but it's actually, the reason why it's confusing is because it's simple. Because think about it, so if I have, a number is getting smaller on top, right? 0. The top is going towards 0, right? What's happening with the bottom? The bottom is getting bigger, right? So what's the limit? Nope. It's 0, right? No, I mean, just think about it. So let's say, for example, okay, think about this, right? So you have something that's going towards 0 on top and infinity on the bottom, right? Okay, let's say I had the number 5, and then the bottom is going towards infinity, right? Well, what's that? Well, that's obvious, right? So notice that you don't even think twice. That's 0, right? That's like, oh, of course that's 0. Duh, right? I mean, you've done that 20 million kajazillion times, right? But for some reason, well, is 0 over infinity bigger or smaller than 5 over infinity? It's smaller, right? I mean, so it's going to 0 even faster than 5 over 0 is, right? But for some reason, your brain gets confused because there's zeros, infinities, and then you start thinking of it in terms of like rules in your head. But you don't want to think about it as rules in your head. Just think about it logically, with what you know, with what makes sense. And so if on top you have a constant, right, and the bottom is going towards infinity, where's that function going? It's going to go towards 0, right? No matter what the constant is. The constant can be 0 or 1,000,000, but that's still going to 0, right? Does that make sense? Okay. All right. So this would be 0. Okay. Okay, so good times, right? So, oh wait, I'll keep this here. 0 over infinity. Okay, so any other questions with that one? No? Okay. All right, let's do another one then. What about if we have, for example, a different kind of indeterminate form? So like, let's say we have something like cosecant x minus 1 over x. Okay, so cosecant, maybe it'll help if we think of it as, what is that, 1 over sine? Okay, good. So as x goes to 0, where does 1 over sine of x go? Okay, where does sine x go? 0. So 1 over 0, that's going to be infinity, right? You have 1, a constant on top. The bottom's going towards 0, so then it's going to be infinity, or if we want to keep it simple, let's just do 0 from the positive direction. So then it's positive infinity, right? It doesn't really matter, but but in this case it doesn't really matter. But then what about 1 over x? Also infinity, right? Okay, so then what do I have? This is infinity minus infinity, right? Okay, so this is infinity minus infinity. So is that indeterminate? It is indeterminate, right? Can I use L'Hopital's rule? No. Why not? Because it's not 0 over 0 or infinity over infinity. So that, again, that doesn't mean that we cannot use L'Hopital's rule on this entire problem. It just means we need to do some algebra to rewrite it. And if you are subtracting two functions that are fractions, well, the most obvious thing to do would be to combine them into one, right? Because that's how L'Hopital's rule is written anyways, as a fraction, right? So then combine them is the logical step. So, okay, so let's do that. So if I combine them into one, what's my common denominator? Sine x times x. Well, you kind of have the option, I guess. Do you guys want... Okay, so you have to decide, though. Do you want to use 1 over sine x, or do you want to use cosecant x? What would you prefer? It doesn't really matter. I mean, you know, it's just preference. The thinking ahead, you're going to have to get its derivative, right? So I don't have a preference, honestly. I'm not trying to trick you guys or anything. Okay, so I think you're saying to leave it. What is it? We'll just leave it. So x cosecant x minus 1 over x, right? So common denominator x, put them together. Yes? You with me? Okay, so the other option would have been no, because it would have been, so here, I'll write it down and then I'll erase it. So it would have been this, right? 1 over sine x minus 1 over x, which would be, so it would be x, what? X minus sine x, right? So now looking at them both, I don't know, which one looks nicer to work with? They kind of look the same, right? Because you have to do the product rule no matter what. I don't know. It's kind of a toss-up. Well, the thing is, you don't know until you take like 1 or 2 steps anyways, so then, okay, we'll just stick with what we've wrote down first. Okay, so now, question, can we use L'Hopital's rule? So what do I get here? X cosecant x, that would be, what is that? What's the limit as x goes to 0 of that? Nope. Does that look familiar? That's 1, right? That's the very first example we did, just the reciprocal of it, right? Or if you just do L'Hopital's rule once on that, that's 1, right? Get the derivative of the top and bottom, you get 1 over 1, right? Okay, so this is 1 minus 1, which is 0 over 0. So that means that we now can use L'Hopital's rule on that one. Does that make sense? You with me? Okay. All right. So let me erase this again. All right. So now, so let's do this here. So this is equal to. Let's see. I might need a little bit more room. So I'm gonna write down the equal sign down here a little bit. Okay. So this is equal to the limit as x goes to 0 of, well, the bottom's just 1, right? The derivative of x is just 1. The derivative of x cosecant x, what is that? That's going to be 1 cosecant x, right? And then plus x times the derivative of cosecant x. What is that? Close? Cotangent. It's the same as secant, except it's minus, and then it's the cos instead of the c's. Right, instead of secant tangent, it's cosecant cotangent. Okay, and then minus the derivative of 1, which is 0. Okay, now does this look better or worse? It looks worse, right? So hopefully this actually turns into something, but without much else to do. Can I simplify this in any way, shape, or form? We should probably try. A good way to simplify is to rewrite in terms of sines and cosines. So, for example, here, see how there's a... Well, what should we do? Well, yeah, if we do, if we rewrite it all in terms of sines and cosines, we get plus, well, let's do minus. So cosecant is 1 over sine x, right? And then cotangent is sine x, cosine x over sine x. Well, it's not very good, is it? Not very good at all. Let's see. What can we do? What do you guys think? Well, we have to be able to do something. Okay, how about, what do you guys see? Do you guys see anything that we can do?
Factor out the 1 over sine x.
That is an option. Let's do that. Okay, good idea. Now, what would I have left over inside then? 1 minus x cosine x over sine x. Okay, so, all right, well, this looks bad, but let's look things over here. Oh, this is bad. Yeah, this is bad. What is it? This is bad. Okay, so what is this? So this, notice, but this is a good learning experience. Okay, what is that limit? That's 1, right? So the limit of, as x goes to 0, of x over sine x, we just wrote that one down, right? That's the number 1. Okay. Now, what's the limit as x goes to 0 of cosine of x?
1.
That's also the number 1, right? So what do I have in the big parentheses? Okay, so this is 0, right? Over, what's the limit as x goes to 0 of sine of x? Also 0. That is right. So what just happened? Notice, okay, notice, this is good. This is a good example because take a look at what we started off with. I have that, right? Now take a look at what I have. It's still indeterminate, which means the only way forward at this point is to do L'Hopital's rule again, right? But now I would be doing L'Hopital's rule on something that is worse than what I started with, right? Okay, so what do you do then? Yes, you do not keep going. Because if you keep going when it gets worse, what do you think is going to happen? It's going to get even more worse. Yes, exactly. Okay, so this is important to recognize. So here at this point you go, okay, I'm going to scratch that. And then what do? You go back and you go, hey, I remember I had an idea to turn everything into sines and cosines and take a look at it there, right? Okay. All right. So let's go back. So does that make sense? There are another time when it gets more complicated too is when you have radicals. A lot of times if you have a big radical, you get the derivative. Remember, if you get the derivative of radical every time, you get another radical, right? So if you keep doing that, well, then it's just going to keep making it worse and worse and worse. So that's another case where it's not recommended to do L'Hopital's rule. All right, so back to the drawing board here. So what are we going to do? Sines and cosines, right? Okay, so erase all this stuff. Erase everything. And start anew. Alright, so then this is going to be equal to the limit as x goes to 0. So what did we say we had? We had x sin x. Notice that we didn't really know if it was going to work out or not, right? So we gave it a go, and then if you see that it's making it worse, as long as you didn't make any mistakes, then yeah, just go back and kind of look for a different path. So okay, so now if I do L'Hopital's rule now, what would I get here? Oh.
1 minus cosine x over sine x plus x cosine x.
Over sine x plus x cosine x. So that's much better, right? Okay, now, can I simplify anything? How about this? No, that's a mad slasher moment, right? We do not want to be doing that. All right, so what do I get here? Is there anything I can do? Anything I can simplify? What cosine x over the x? What are we talking about?
1 minus cosine x over x.
That is a limit that we know, but we can't. Well, we could if you wanted to divide top and bottom by x.
Can't you factor out the x and then
What is it?
factor out the x in the denominator?
Factor out the x in the denominator, but there's only...
You can't use the identity and then like use the identity.
So you're saying factor out an x here, and then what would I have? I would have sine x over x plus cosine x, like that?
What?
Funny factoring, as we like to call it. Do you guys agree that that's a correct factoring of the denominator? If you multiply the x through, would you get the denominator again? Sure you would, right? It's funny factoring, but that's okay, because in calculus we often have to do funny factoring. Is that helpful? I don't know if that's helpful.
Sine x over x is 1.
Well, I'm thinking if, let's see. Well, the thing is, I see something, but I'm also curious what doing another L'Hopital's rule would do. But I don't know if it would make it better. Should we try? Okay, so this is a try. I mean, I can tell you how to evaluate this. But I don't know if most people would have seen it. Would be able to recognize it. It's like one of those. I mean, I could recognize it because I've taught the class like 50 million times, So, but you guys are taking the class, for your first or maybe second time. Hopefully not third. Anyways, let's just try to do the L'Hopital's rule again. Yeah? Just to see what happens? Is that okay? Okay. All right, let's try. Because it's still indeterminate, right? You guys agree that it is indeterminate? You have 0 over 0, right? Okay. So let's just see. Let's see where this takes us. Okay. So derivative of the top. Sine x, right? Derivative of the bottom is plus product rule again, right? So cosine x plus x, well, it would be minus sine. Yeah, so it's going to be minus sine x, so might as well just change this to a minus x sine x, like that, right? Let's see. Yeah, see, that's better. That's easier. Okay, if you want, I can show you what I was talking about. But so this actually works because what do I have here? I have sine of x, right, on top. On the bottom, I have 2 cosine x, right? And then minus x sine x. Okay, now this looks worse than what we started with, but it's actually not, because what do I have on top? This goes to 0, right? Cosine 0, 0. Okay, now what is x sine of x? As x goes to 0, that's going to go to 0. But notice what's cosine of 0?
1.
That's 1, right? So this is different than what we had before. This is 0 divided by 2. Is that indeterminate? Nope, that's just 0, right?
Why is x sine of x going towards 0?
Because x goes to 0, and sine of x goes to 0 too. So.
What was the first part that you were talking about?
Oh, do you guys want to see? Well, it's because, yeah, the reason why I hesitated is because it involves remembering a couple things. So basically, if you rewrite, so you don't have to do this anymore, but just for fun. So if you rewrite, so if you do this funny factoring, right? Notice how I can rewrite this as the limit as x goes to 0 of 1 minus cosine x over x, taking this x with the numerator there, like that. And then all that divided by, so this is just a rewrite. I'm not really doing anything here. Over sine x over x plus cosine of x, right? So I didn't really do anything. All I did was that little x that I factored out, I just put it with the numerator. And then rewrote the denominator, right? Is that okay?
Using identities?
No, just a little algebra. Just rewriting. I mean, you know, like if I have, for example, I mean, it looks complicated just because there's a lot of stuff going on. But, you know, if I have A over B times C, for example, isn't that the same as A over B divided by C? It's the same thing, right? So that's all it is. You know, so this B that's down here, just put it on the denominator of A. But that's all it is. But anyways, what is this limit? That's 0, right? You can either remember one of the limits that we did back in the day, right? Or just do L'Hospitals Rule once on that, just by itself, and you get 0. And then what's this limit?
1.
That's 1. And what's this one? So 0 over 2, which is 0, right? So it's faster if you recognize it, right? Which, you know, most people probably wouldn't. But maybe if you look hard, you know, if you're looking hard for it. But most people probably just say, oh, I'm just going to try L'Hospitals Rule again, and then hope that it works out. But yeah, I mean, notice that it's okay to not really know exactly where you're going. So you'll see this as a recurring theme in calculus, and it only gets more recurring as you move forward, where you have to be comfortable with not knowing exactly where you're going. You know, I just picked out this problem kind of randomly. I grabbed it from the book, and I'm like, okay, well, let's try it out. You know, it's not like I knew it already or anything. And you know, as we go, it's like, oh, you can go try this, try that. And that's exactly how I do it, because that's how you would approach it as a student. If I just come up here and tell you exactly how to do, you know, a problem step by step, well, you know, that's fine for that problem. But what about when you go home and do other problems? You need to kind of have a strategy for attacking the problems, right? Does that make sense? So, okay. So any questions? No? Okay, you guys ready to step it up a notch? A little bit more? Okay, all right. So all right, so this is going to be a little bit more difficult. Okay? A little bit more difficult. How about well, that's okay. All right. Okay, so we have the limit as x goes to 0 of e to the x plus x raised to the 1 over x. Okay, so what do we get when we evaluate? So e to the 0, what is that? 1 plus 0, which is 1. Okay. 1 to the infinity, right? All right. What is that? That's indeterminate, right? One thing to keep in mind, all the time I get students tell me, well, that's just 1. Why is it not the number 1? 1 raised to any power is 1, right? Isn't 1 raised to any power equal to 1? If you multiply the number 1 by itself by 1,000 times, 1,000,000 times, 1,000,000,000,000 times, 1,000,000,000 times, infinitely many times, what do you get? If you multiply 1 by itself infinitely many times, what do you get? You get 1, right? Okay, why is this not 1? Well, infinity isn't a number, yes, but you agree that if I, for example, multiply 1 times 1 times 1 times 1 times 1, and I keep doing this forever, you guys agree that this is going to equal to the number 1? Okay, good. Okay, but then I have this. Okay, so you're right on that. So, but here I have 1 to the infinity, right? 1 to the infinity, that's what you guys told me. But I'm telling you this is not just 1, that this is indeterminate. Why? So when we have, for example, 0 over 0, are we actually dividing 0 by 0? We're not really dividing 0 by 0, right? Or if I have, for example, 5 over 0, and we go, oh, well, what is that? That's infinity, right? But are we saying that 5 over 0 is infinity? No, we're saying that the limit as x goes to 0 of 5 over x is infinity, right? So here, this 1 to the infinity is not really the number 1 multiplied by itself infinitely many times. What you have is this inside the parentheses, that's approaching 1, right? So that the inside of the parentheses is approaching 1, and then as it's approaching 1, the exponent is approaching infinity. So those two things are interacting, so they're not just static. It's not just one number that you're multiplying it by itself. This inside is approaching 1, and the exponent is approaching infinity, so that will potentially approach some other number. That is not necessarily 1. Okay, so does that make sense? Okay, good. Sort of, at least. All right, so I only mention it because all the time I get students telling me that 1 to the infinity is 1. Okay, so let's see. So let's see. What did I write down? X plus, no. E to the x plus x. All to the 1 over x, right? Okay, all right. Now, so we said this is 1 to the infinity. Now, does this look like I am going to be able to use L'Hopital's rule? Well, not really, right? It has to be 0 over 0 or infinity over infinity. This isn't even close to that. So what can we do? Well, what does this kind of look like? If for example, if I cover this up, does that kind of function look familiar? Where do you remember seeing functions like that? With logs, yes. Notice you have a function and you're raising it to the power of another function.
Work it inside out.
No, when did we do stuff like that with functions raised to functions? Well, logarithmic differentiation, right? Remember when we were getting derivatives of function raised to other functions, we said, oh, well, we don't have any rules to deal with this. What do? We can do it using logarithmic differentiation. Okay, so it's similar. You're not really doing logarithmic differentiation, but it's a similar idea. You want to use logs so that you can bring the exponent down and allow you to manipulate it. Because that's really the issue, is you have this exponent that's a function. The base is a function, so you can't really work with it. So, okay, so what you do is you just use the identity. So you use the following identity. Basically, y is equal to e to the natural log of y. Okay, so you guys remember that identity, right? So we did this back a little bit ago. Okay, so in this, what is this y business? Well, this, what you're getting the limit of, this is y. So you're going to rewrite your limit. So basically, if I apply this identity here, I'm going to say, okay, this is equal to the limit as x goes to 0 of e to the natural log of y, right? So in this case, e to the x plus x to the 1 over x. Okay, so do you guys agree that the left side is equal to the right side? And all I did was apply the identity. And if you follow the colors, then it makes sense. Yeah. Right? So the y is in the blue, the e to the ln is in the red. And all I did was plug in the limit that I'm looking for, I plugged it in there, right? Okay. So then what we're going to do then, so this is going to be our strategy. Okay, strategy. So what we're going to do is we're going to evaluate the limit as x approaches 0 let me move it down here. Okay, evaluate the limit as x approaches 0 of natural log of e to the x plus x to the 1 over x. So what I'm looking at is this right here in the purple. So I'm going to evaluate that limit. And the answer will be e raised to whatever I get from here. Blah. Whatever it is that I get when I do that. Does that make sense? The strategy? So basically you have, so whatever your function is, right? You're going to get the limit not of the function, but of natural log of the function, which, what's the whole point of throwing in a natural log in there? Well, because that'll allow us to move the exponent down, right? And then once we find that limit, then what's my answer? It's just going to be e raised to whatever we get, right? Because basically we're evaluating this in the purple right here, right? So all this guy, this limit, and then so then my answer is e raised to that power. Does that make sense? Yeah. So there's it's kind of a lot of stuff, but it's very similar to logarithmic differentiation, you know. So okay, so are you guys ready to do this? Yes, no? Okay. So let's try here a little bit. Let's do some, let's see. Of course. Okay. All right, I'm going to do it on a different page because that one broke for some reason. Okay, so we have the limit as x goes to 0 of the natural log of e to the x plus x to the 1 over x. Okay, so first thing we do is we're going to bring the exponent down, right? So this is going to be 1 over x times ln of e to the x plus x. Okay. And at this point, you can check it to see if it's indeterminate, but it's pretty much guaranteed to be indeterminate. Because if it was indeterminate to start with and you just rewrote it in a different way, well, it's still indeterminate because you haven't changed the function. But you can check anyways, just for fun if you feel like it. So, because see, what do you get here? You get 1, right? E to the 0 is 1 plus 0. What's ln of 1? 0, yep. Over 0. So, okay. So, let's see. All right, so then what is this equal to? Can I use L'Hopital's rule? Sure you can, right? All right, so what's the derivative of, let's see the bottom. The derivative of the bottom is just 1, right? Because it's just x. And then what's the derivative of the top? Almost. 1 over e to the x plus x times? 1. Nope. But both what you guys told me earlier.
Oh,
plus 1, right? So it's e to the x plus the derivative of x, which is 1.
Can you go back really quick? Why are we doing the L'Hopital?
Because we were trying to evaluate the limit.
Did it equal 0 over 0? Or?
Yeah. Yeah, it did, right?
Yeah, I don't know.
Because
I was
okay. Yeah, because remember we said so e to the 0 is 1, right? And then this is 0, so it's ln of 1 over 0, and ln of 1 is 0, so it's 0 over 0. Yeah, so when you're doing these, I mean, you check, but at the same time, if it was indeterminate to start with, it's going to be indeterminate again, you know, because, like I said, you haven't changed the function, so you don't lose anything from checking. But okay, so now what? Is it still indeterminate? What is that limit? I get, if I plug it in, e to the 0 is 1, right? Plus 1 over 1 plus 0, which is 2. Okay, so then what's my answer? E squared, right? E to the power of 2. So why is that? Well, remember, what is it that we just found? We found this in the purple, right? We found the purple. And so then our answer is e raised to purple, right? Okay. E raised to purple. So let's just kind of write it down. So I have the limit as x goes to 0 of, so I'll write down the whole thing so that we kind of have it. So e to the x plus x raised to the 1 over x, that's equal to the limit as x goes to 0 of e to the natural log. I'm just kind of rewriting it so that we have it all in one place. Okay. And then this is equal to e. So this right here, this limit, this is the one we just found, right? That too corresponds to that limit, right? The limit as x goes to 0 of then ln of all that stuff. So then the entire limit is e squared. Does that make sense? All right, so questions? No? You guys are okay? Yes.
So the step where you evaluate the limit as x goes to 0 of ln of e to the x plus x, and you disregard the e, that seems wrong to me. I don't know how. I don't know what my question is.
Well, no, yeah, I understand. Yeah, so it's from, so it's been a while since we did this, but so you have the, so one of the limit laws was that, so if you have two functions, f and g, and if their limit exists, then the limit of the composition of the two is equal to f of the limit as x approaches a of g of x. So we use this so much without mentioning it that we forget that it's true. But for example, like anytime you have, like for example, let's say I have the limit as x approaches 0 of, say, sine of well, I don't know, pi e to the x, for example. How do you actually evaluate this limit? That's kind of like our quick way to do it, but really what you're doing is you're using this limit law. You're really saying, okay, well, evaluate the limit of the inside, and then whatever number you get from that, plug it in, right? Isn't that what we always do? We don't write it out this way, but this is really what we're doing, right? Because when we plug in the number, we're really, the reason why we plug it in is because we're evaluating the limit that way, right? So what's the limit as x goes to 0 of pi e to the x? Well, you plug it in, right? And in that case, you would get pi, right? And so then what would you? Well, then you evaluate sine at whatever you get there, right? So it's exactly the same thing, right? Here, I have e raised to this stuff, right? Well, what do I do? Find the limit of the inside, right? And then whenever I find that, well, then plug it in. So it's no different. It seems like you shouldn't be able to do it because it's so big. You know, you like look at it and it's like, oh, it's no way that we can just do that, you know. But it's really no different than you know the stuff that we usually do. Any other questions? No. There are no dumb questions. Actually, there are, but go ahead, ask. I'm just kidding. Go ahead.
Like, I understand when we did the logarithmic, the way we did it with the ugly derivatives, but why is it e to the ln?
So all we're doing is we're applying this identity here, this one.
Right, but I understand the ln of everything, the limit, but where does the e come from? Why is it?
Well, so this is one of the identities, but the standard one is a to the log base a of, say, x equals to x, right? So all you're doing is you're saying, okay, well, I'm going to take this which I don't know how to evaluate, and I'm going to rewrite it like this and hope that it'll work out instead. That's all you're doing. You're just rewriting a different way. And the reason why it does work out is because rewriting it with the log allows you to take the exponent and bring it down. That's really what helps you, you know. Any other questions? No? You guys want to take a break? Yeah. Okay.